All right, well, thank you very much, Lisa. And it's a pleasure to come back here. I gave a talk here a couple years ago. I got invited back already again, but I tell you why, Moran, I gave this exact talk. I did improve a couple slides, made a few updates, but for the most part, I gave this exact talk 6 months ago at the Everglades National Park. Now, at that presentation, it's a monthly presentation they have, or a monthly seminar series. They usually broadcast them to the whole state of Florida, but their computer didn't work. So I basically gave the talk to 60 people who were sitting there in front of me, but that was the only audience. So as a result of that, Moran suggested, well, why don't you give the talk here so that we can give our message up here of what we are doing about saving the planet from all those nutrients that are out there. So the title I have is Using Wetlands to Prevent Phosphorus and Nitrogen Pollution in Downstream Wetlands, Lakes, Rivers, and Coastal Waters. That's a big title. And I even have a subtitle. Again, the MOM River Basin, I'll tell you what that is, Gulf of Mexico / Laurentian Great Lakes, Florida Everglades Challenge. Now, all of you will appreciate the word challenge, I think, because the grand challenge, as you're probably all aware of, is a $10 million prize that will be given out in 2022, I understand, from the Everglades Foundation for someone who can figure out how to protect the landscape from phosphorus. So what I'm saying is this whole issue is broader, much broader than just the Florida Everglades, but the Everglades is sort of the showpiece of and I'll talk about the Everglades and phosphorus as one of my case studies. So I'm going to be talking about 3 different case studies that relate to the retention of nitrogen and phosphorus by wetlands to save downstream ecosystems. Well, nitrogen and phosphorus. We all know what they are. We all know they're limiting nutrients. We all know they're in fertilizer bags. When you get a fertilizer bag, it says NPK. Nobody gets excited about the potassium, but nitrogen and phosphorus very definitely are causing all sorts of problems on our landscape. Of course, they're 2 most essential elements of life. They're right up there in the top 15 elements that we need for our nutrition and for our sustenance. Nitrogen is the basis of amino acids, which is the basis of proteins. Phosphorus is a basic ingredient in the energy system of the adenosine triphosphate power system in our cells. I'm very fond of using the Redfield ratio just to put things in balance. Redfield ratio, for those of you who don't know what it is, it's a ratio of carbon to hydrogen to oxygen to nitrogen to phosphorus of plankton in the sea. But it's basically the ratio of those chemicals that we find in life. So it's a CH2O, which basically if you multiply each of those by 6 is glucose, but also an amount of nitrogen, an amount of phosphorus. And so you don't have to do the calculation. I will do it for you. The molar ratio, the ratio in moles of carbon to nitrogen and phosphorus in living organisms is approximately 106 moles of carbon to 16 nitrogen to 1 phosphorus, okay? So each is like an order of magnitude. But the weight, that's what we can understand better, you know, grams or pounds or whatever. The weight ratio is 41 grams of carbon to about 7 grams of nitrogen to about 1 gram of phosphorus. Okay, so phosphorus is the least needed, nitrogen middle, and carbon much higher. And that's basically for our overall metabolism for what we are made of, what organisms are made of, what plants are made of, okay? So that just puts the 3 in sort of a ratio. I'm not going to talk about carbon. That's a whole issue in itself. I mean, that's gigantic. But we're going to talk about nitrogen and phosphorus. So why are we calling them pollutants? They're so essential to life. They're so incredibly important for us to live. They become pollutants. And I guess you could think of CO2 as in the same category now, right? We breathe out CO2. That makes us polluters. So things have changed because of the excessive amount of chemicals we have in our biosphere relative to what it used to be. This is a graphic from the World Resource Institute, and every dot indicates a problem of excessive nitrogen or phosphorus. You know, and you can just see the dots are splattered over southeastern United States, the eastern seaboard, the Great Lakes. Europe's just covered with dots. And China's getting up there with a lot of eutrophic systems as well. These are places where either nitrogen or phosphorus is really changing aquatic ecosystems dramatically and for the negative. My friend Jay Martin at the Ohio State University, we were working on a proposal together, said more than 750 aquatic ecosystems worldwide currently suffer from degraded ecosystem services due to urban and agricultural inputs that cause water quality impairments such as hypoxia, dead zones, and harmful algal blooms. Those are the terms we use for them. And of course, down in Florida here, we have other terms for what's going on, but it's basically the pollution of the Florida Everglades. So these have become serious problems worldwide. What I'm going to just talk on is 3 of those 750 dots, okay, but 3 that are in the eastern half of the United States. I do often make a point, and people are shocked when I say this, that I think this eutrophication of the planet, where we've absolutely doubled the amount of nitrogen, biologically available nitrogen on this planet, since in the last century, let's say. We've increased the CO2 by about 38%. I argue that this eutrophication of the planet is showing signs already now that it is much more pervasive and, how shall we say, obvious effect of human beings on the planet than is the change in climate. The change in climate is subtle. That will happen over a long time, but we're here and now just polluting the living daylights out of our aquatic systems. It is horrible, and it hasn't gotten any better, and it continues to get worse. So I'm arguing this is one of the most serious aquatic problems that we have on this planet. Now, wetlands, that's what we deal with, so that's what I'll be talking about, provide a lot of what we call now valuable ecosystem services. We used to just call them values, but ecosystem services is really stuck. And it's services such as water purification. I'm using the terminology of the people who really put ecosystem services on the map, the Millennium Ecosystem Assessment. Water purification, flood regulation, storm protection, biodiversity, islands and corridors, climate regulation, especially through carbon sequestration. I won't talk about that today, but it's gigantic. And then just in a more general sense, locations for human relaxation and nature observation education. Well, this is the one we're going to be talking about. The ecosystem assessment, they use the term water purification. By the way, if anybody's from up north, I've used this sketch for years. This is sort of a restoration we were talking about for the lower Cuyahoga River in Cleveland. Anybody from Cleveland? That's supposedly in the horizon. You can't see it, the Cleveland skyline. Do you recognize it? Okay, so the first one I'm going to talk about is one that I've been involved with for 20 years or more, and that is this idea of saving, it's related to our Gulf of Mexico, which is right out here, right out the side door here, but it's creating and restoring wetlands for reducing nitrogen pollution to coastal ecosystems. This is probably one of the biggest eutrophication issues in the United States of America. It has not diminished in the last 20 years since I've been following it and working on it. But basically, this area south of Louisiana has an area of anoxic conditions that has been referred to by the scientists as hypoxia. Now, hypoxia is when the oxygen goes below 2 milligrams per liter. If the oxygen in your fish tank goes below 2 milligrams per liter, you can kill a lot of fish. So that's sort of considered to be a threshold for aquatic life, and that's been referred to as hypoxia. If it goes below 0, it's called anoxia. So hypoxia is almost anoxia. But the press doesn't understand all these fancy words, and they refer to this hypoxia as the dead zone. So this is the seasonal dead zone in the Gulf of Mexico. Did you all know this happens? I mean, it's gigantic. It's about the size. Okay, here's how they used to describe the size. They used to say, well, it's the size of the state of New Jersey. Anybody from New Jersey? Are you insulted? But then we got a USDA EPA administrator from New Jersey. And all of a sudden we were supposed to say, well, it's about the size of Massachusetts, because that was a Democratic state. Now we're back to saying New Jersey again. So just to give you an idea of how big that hypoxia is. Well, where's the cause? There's so much debate in the scientific literature on this now. I'm not even going to say there's a definitive connection anymore, but clearly, America's breadbasket, and this pink area shows where the excessive amounts of nitrate and nitrogen occurs in the streams. You know, the graph changes a little bit every year, but this was from some years ago. But that's America's breadbasket. That's where we have corn and beans. And that's where we just plaster the landscape with nutrients. That's where I was, up at Ohio State, in the middle of that. And so the connection between that area of the source of the nutrients and this, the cause, it took a lot of convincing to tell people this, yes, that's probably what's happening. They're separated by 1,000 kilometers, but the source of the problem and the problem itself are very definitely connected. So for the last my gosh, it's probably 25 years now, our federal government, in its infinite wisdom, you know they have infinite wisdom, the federal government has tried to figure out how to solve this hypoxia problem, you know, politically and not getting people mad and all that, and it just hasn't happened. And I'll explain. This, for example, these are graphics. That's the coastline of Louisiana I'm showing in each of these three pictures for 2011, 12, and 13. I do have 14, and I think we have 15 now. These are maps that were developed by Nancy Rabelais at the Louisiana Marine Consortium. It's affiliated with the state of Louisiana, and she's been going out every year and measuring the size of this hypoxia. Now they do two press releases. They do a press release before she goes, and they predict the size, and then they go out and measure it, and then she does another press release about mid-July, early August, of the actual size of the hypoxia. And I'll show you a graphic of that in a minute. So it changes in size. And for example, you can see, well, they must have solved the problem because in 2012, there's no hypoxia, or it's 1/2 the size. It's hard for you to remember, but 2012 was when we had a gigantic drought. There was no Mississippi River. That's when the barges were getting stuck and the river wasn't flowing and everything. So that almost makes the point. When the Mississippi River wasn't flowing, the hypoxia was much smaller. Because there are a lot of other competing theories of why the hypoxia occurring, including the idea that it represents sort of the melting of Louisiana. Louisiana is melting into the sea. It's a euphemism I use. The oxygen or the organic matter is just disappearing. The sediments are decreasing. The wetlands are decreasing. I think they use a term that a football field, they relate to the Louisiana people by saying a football field size of wetlands disappearing every day. So they're losing wetlands, and there are people who are theorized that losing of the wetlands is what's emanating or causing organic matter that's coming and causing this. So there's all sorts of theories, but nevertheless, there is an absolute connection between the nitrogen and the hypoxia as well, in my view. Well, we studied this for a bunch of years up at my little wetland up in Ohio State. I moved down here because scientists would come up from Louisiana or Florida and so on and say, Bill, your wetland's cute. So I had a couple of cute wetlands up in Ohio, and we did a heck of a lot of research on them, including looking at the effect if we were to create wetlands in the Midwest, can you take nitrogen and phosphorus out? But in our case, we were interested in nitrogen. Those two kidney wetlands have more papers per square meter than any wetlands in the universe. I swear. We should do that calculation. Papers per square meter or papers per acre. So those are the ones that we've intense information about the hydrology, nutrients, and so on. We summarized everything. We did an entire brain dump with all my colleagues and everything that was just published a year ago. In fact, it was published November 2014. You can't read any of this, I know, but it's published in Ecological Engineering volumes, and the entire volume 72 is a special issue called, I can read it for you, the Olentangy River Wetland Research Park, 2 decades of research on ecosystem services. That's what it was all about. What does nature do for you? What can wetlands do for you? You know, it's funded by a ton of different agencies over 20 years. But if we jump straight to nitrogen story, this is the overall nitrogen budget for those 2 wetlands over about 17 years, I believe. And we were able to calculate a very tight number with a very short error bar. Each number, by the way, is an entire year. So it's not a sample, it's a year. So we have like 17 years in that number, times 2 wetlands, that would be 32. I'm not sure of the N in our calculation, but we're pretty tight on what we think a wetland can take out as far as grams. The units are grams of nitrogen per meter square wetland per year. And that suggests about 40 grams nitrogen per meter square per year is a reasonable thing to ask nature to do. I mean, those are gigantically important numbers to me, but it took 20 years to get it. We also did a whole bunch of other studies on nitrogen. I'm just giving you 2 illustrations here. We did entire nitrogen budgets with all the fluxes, including denitrification, and so on. Interestingly, we found that the biggest sink of nitrogen in these wetlands was not denitrification, which many of you know is when it goes up into the air, but it was actually sedimentation of organic matter. You know, it was these wetlands were basically sequestering nitrogen. They were also sequestering carbon too, but so, and then denitrification patterns, we had all sorts of graduate students doing that for theses or dissertations over the years, and it shows a very distinct pattern of being, of course, higher in the summer when it's warmer, so it's very temperature influenced. Anyhow, there's just more data we know what to do with on those processes. But what we did earlier on, when we had some data from our site, from other sites in the Mississippi Basin, is we developed these very simple models that allowed us to take that inflow to a typical wetland, let's say, and if we put it scatter plots, we were able to estimate the percent retention that's possible in your typical wetland in the Midwest, I guess you'd call it. So from this model and other calculations, we were able to calculate the basic question is, I always get is, well, Bill, how many wetlands do we have to build in the Midwest to save the Gulf of Mexico? So by using an estimate that we have to reduce the nitrogen in half, and by the way, this graphic was published in Bioscience in 2001. It's the most used slide I've ever had. It shows what we need to do in the Midwest to fix the Gulf of Mexico. You're not going to fix it down in the Gulf of Mexico. You're not going to spray copper sulfate in the Gulf of Mexico. They're just not going to be able to handle it that way. They're going to have to solve it at its source. And we suggested, of course, better fertilizer management. That goes without saying. But that in itself will not solve the problem. And I was at a land-grant institution. I can't say shut down modern agriculture in the Midwest or I would have gotten thrown out. But besides, that's just not a viable solution. So we said you can make some impact by better management of fertilizers on the landscape. But quite frankly, what we need are these buffer systems between the farms and the streams. So there should be wetlands and bottomland forest in between every farm and every stream, ditch, or creek. It should be the law. If I was czar of the Mississippi Basin, I would declare that. And by the way, we call it the Mississippi-Ohio-Missouri Basin for 2 reasons. Ohio sort of gets the short shrift because we send all the water down to Louisiana. The Ohio River is twice as big as the Mississippi when they come together. So that's just not fair. And the second thing is because we love that acronym, MOM. So someday we'll get a president, maybe we can sneak it in with Obama before he leaves, president declare right before Mother's Day, we're going to save the MOM River Basin, the Mother River of America, make a big deal of it and start building these wetlands and start getting that hypoxia down to a reasonable level. What do you think? I mean, that just makes so much sense, it's ridiculous. But we're going to, that's the kind of thing, Anybody that does national politics, let's do this. So the number at the bottom is our calculation, our very rough calculation of what you need. 2 million hectares, but I'll translate for you. We need 5 million acres of wetlands in the Midwest to make a dent in the hypoxia downstream. Now you all are sitting down, so you didn't fall down. That number sounds enormous, but really it is a very small percentage of the watershed. If we focus it in the Midwest, it might be 5% of a watershed, for example, 7%. If we average the entire watershed, which includes areas that don't have high nutrients, it would be about 2%. So we need about 5 to 7% of our landscape working for us so we can continue to produce food in the Midwest and have a healthy Gulf of Mexico. I mean, that just makes sense. Well, I got to show you the story of has it happened. Well, this is a graphic that Nancy Rabelais published, and this goes through the year 2014. I don't have the updated to 2015. This is the size of the hypoxia. Now, I have to tell you that all these studies were going on about the year 1999, 2000, right at the turn of the century is when all these studies were happening, the initial ones. That didn't happen in 89, that happened in 2000, but the federal government, again, with infinite wisdom, declared that we shall have a hypoxia no bigger than 5,000 square kilometers. Okay? They declared it in 2000, published it, said that's what we should do. Well, in the year 2000, you can look, it went below 5,000, and they were probably ecstatic. I don't know. You know why it went below 5,000? There was a big hurricane that year. It stirred up all the water. So hurricanes will solve the problem, by the way, of hypoxia, but I don't think New Orleans wants to hear that. So we have to find a better way to solve this hypoxic zone. Well, we did our recommendation was published about then. The recommendation I just gave you, that we have to build all these wetlands. And I'm sorry to say, even the last 5 years, well, this goes through 2014, the average is not 5,000, the average is more like 15,000. We have not even come close to solving this problem. But nobody's watching it, probably except me. I mean, it's just lost from everybody's radar. They've gone on to other questions. There's still a hypoxia task force that meets every year somewhere in the Midwest and blah, blah, blahs about whatever, but they just don't have any capability of doing this solution we suggest, or any other solution to solve this problem. And one of the reasons it got exacerbated is because of energy, because we're basically growing corn now in the Midwest, not just to eat, we're growing corn for ethanol. So every square meter of the Midwest now has corn or beans growing on it. And so that just really put things backwards. But anyhow, that's the story on a long-range idea, a solution to a big pollution problem, and how we really don't have the will as a nation to solve big problems like this. Maybe we will someday. Or if you think that one was fun, this one is one that's just on the drawing boards, and I'm just going to show you real quickly. It's also up north. Restoring the black swamp in Ohio for mitigating harmful algal blooms in Lake Erie. It was just when I was leaving Ohio, this was in 2011, for example, that all of a sudden, it was like a bad dream to everybody. Lake Erie, you all know where Lake Erie is, north of Ohio? Lake Erie is the shallowest of the Great Lakes. It's always the one that was the signal that we got a problem before any of the other Great Lakes. Lake Erie started turning green again, especially in its western basin. This is an actual aerial photo. This is not somebody's painting. This is what it looked like from the air. It was green as pea soup. And it was a big story. It was published that satellite image was published in 2013 in the Proceedings of the National Academy of Science with a big story of what's going on and so on and so forth. But it really, really caught people's attention, especially especially in Ohio, a little bit in Michigan, and certainly some in Canada, but Ohio is the state that bears the brunt. And there was a nutrient Ohio Lake Erie Phosphorus Task Force. So they immediately decided it was phosphorus. They called it a phosphorus task force. And they decided it was only Ohio. But they declared that nutrient impairment continued to plague Lake Erie, impacting an $11.5 billion industry, tourism industry. Yes, there's tourism on Lake Erie. Always was, right, Moran? You know that firsthand. And it's really gone in the tube in the last 3 or 4 years. It really has this perception. It doesn't matter whether it's real. The perception that that lake is like pea soup is real, and people go elsewhere now for their recreation. So it's, you know, the impact is well into the billions. So you got $1 billion. Okay, well maybe we can take $1 billion to solve it, maybe. And by the way, in 2014, this was just about this time last year. It was August of 2014. That's when the city of Toledo shut down due to a toxic cyanobacteria in the drinking water. Do you kind of remember that? The whole city just shut down, and the mayor said that water crisis was similar to 9/11. And that was published in the Toledo Blade. So they're year in, year out, and the lake, by the way, is green again this year. So they've got this horrible problem of a eutrophic lake. People don't like eutrophic lakes, and I have the perfect solution, but we'll see if they answer. And the other thing is when you do a phosphorus budget, if indeed it's phosphorus. Now, nitrogen is the coastal problem. Phosphorus is fresh water. It's almost, you can take that to the bank. Fresh water, worry about phosphorus. Coastal waters, worry about nitrogen. And yes, there are subtle differences sometimes, and scientists publish papers say, well, that's not always true, but for the most part, I think it's something you can remember. But most of the phosphorus going into Lake Erie was from non-point sources. They were able to control. They spent billions of dollars on taking phosphorus out of treatment plants. They've got tertiary treatment on any wastewater that's going into Lake Erie. So they spent billions on the tertiary treatment. They were very proud that for a few years the lake was clean. And by the way, it was clean because of tertiary treatment, but also because of zebra mussels. Zebra mussels are invasive species. They came in and they just sucked that lake into their gut and cleaned it like crazy. It was the cleanest I've ever seen Lake Erie. Were you there, Moran, or you already left? Crystal, it was like Silver Springs, Florida. It was. I never had seen the bottom of the lake before. Thank you, zebra mussels. The trouble is, they're invasive species, so people didn't like the fact that they were cleaning it up. So, again, it's turned green again. It's due to non-point sources. This is a map that shows that almost all of that phosphorus, that big orange line you see coming in from the right side of or the left side of the diagram, suggests that most of the load comes from the MOM River Basin. I love that. My daughters loved the name of that river when we would drive up there, MOM River. And the MOM River goes through an extensive amount of farmland. It starts even up in Fort Wayne, Indiana, so it comes from Indiana. But all that area that you see it flowing through is just massive fertilized agriculture, but former wetland. In fact, this graphic I got from okay, it's hard for me to explain this to people down here. We have an estuarine reserve on Lake Erie. And when I moved to Ohio, I said, there's no estuaries in Ohio. They almost threw me out of the state because they need it for funding. It's called Old One Creek. It's a delightful place, but I'm sorry, it's not an estuary. It's a freshwater marsh, but you know, they say, well, it has a little bit of a wind tide, and okay, well, let's not argue it. But that's where what I'm showing you, these next two pictures are. The dark green illustrates wetlands in the 1780s. You see that big plaster of green on the upper left? It was all wetland. And it was referred to as the Black Swamp. And there's folklore about the Black Swamp, and there's stories about American armies in the War of 1812 trying to trudge through there up to go do battle up in Canada, and just how impossible it was. And also how impossible it was to go from Ohio to Michigan. And this is a personal joke for those of you who appreciate Ohio State and Michigan. Some people wish that we kept the swamp there. So, but it's gone. That's what it looks like now. There's no wetlands at all. Totally drained. So I was invited by the Water Environment Federation. That's a big, big organization of pumps and pipe people. I'm not sure why they invited me, but they saw that I had made a public comment about this, to write a blog that nobody has commented on because you have to be a member. And the blog was Restoring the Black Swamp to Save Lake Erie. And it basically suggested, look, there are times when we, especially if it's an $11 billion problem, where we can swap out agriculture for wetlands, get the recreational value of the wetlands, get a bunch of birds up there. They could even call it Everglades North if they want. It would be a massive wetlands. But by the way, Indiana's already stolen Everglades North. They're restoring the Kankakee Marsh. Anybody from Indiana? Kankakee Marsh is up near South Bend. You don't know where that is? Well, it's gone. It was also destroyed. Yeah, northwest corner of Indiana. They're restoring that, and they're calling it Everglades North. They're not messing around. So we got two wetlands that are being restored. But really, from a practical standpoint, to clean up the water, to increase the economy up there, to have a beautiful environment, what's wrong with having an Everglades North next to Toledo as opposed to a bunch of farm fields? And, you know, I know. Everybody says, well, it'll cost, $11 billion is a lot of money to play with if that's truly the cost of that pollution occurring. And I guarantee you the wetlands will work. Anyhow, that's our crazy idea. This is what the black swamp used to look like. I'm not suggesting we can bring it all back, but it was basically the western extension of Lake Erie. So that's out there for people to chatter on, and there's a few articles now that are coming out of Ohio on this idea, so we'll see where that goes. So that's a new one. So finally, at 9:40, I get to the one that's most important. Creating, restoring wetlands to protect the Florida Everglades. I'm going to race through the first few slides quickly because you probably know all this stuff. You know the restoring wetland saga, probably better than I do, about the original historic conditions, about the fact that we are now shunting water left and right and destroying our estuaries instead of sending it south. Whole bunch of plumbing now that regulates the Everglades. It's not even close to being what the natural flow is now. And there's this concept, and that's all it is, folks, a concept that we get rid of all that plumbing or simplify it and get the water to go north-south. That's the concept. And you and I are we pay twice because we pay as Florida residents and we pay as U.S. citizens a fair chunk of change, $20 billion for that restoration. Now, I have to tell you, I got in a little trouble when I moved down to Florida here because I had just given a paper in Ohio and I looked at 6 big restorations of the world, and one of them was the Florida Everglades. And I just gave my opinion as a wetland scientist, as a viewer of pollution, and just whether these restorations were working. Well, and these are midterm grades, by the way. This is not a final grade. They can improve by the final, whenever that is. I'll write the paper 10 years from now, maybe. Florida Everglades earned a D+. Well, you can imagine how many calls there probably were to the governor's office. Who the hell is that professor at FGCU? You know, I just know what happened. All of a sudden it got very frigid in certain agencies. But it's absolutely true. They haven't really shown anything. And the reason they got a D+ and not an F really was because they have done one very good thing of improving the water quality that's going into the Everglades. That to me was a plus. And that's what I'm going to be talking about. These are called, they're treatment wetlands in the Everglades. When I came here, I said, oh, you build a wetlands to improve the water in the, I said, Bill, we're not allowed to call them wetlands. They told me that, just like they're not allowed to talk about climate change, then they're not allowed to call these wetlands, so they have to call them STAs. Well, nobody in the rest of environmental civilization, except in Florida, knows what the heck a STA is. So you'll see I published a paper and I just called them wetlands. But they are located, this is Lake Okeechobee, this is the Everglades agriculture area where we know all the phosphorus is coming from the sugar farms and other agriculture. And they've been able to build those, see those light green areas on this map south of the agriculture area? That is approximately, sorry I give it in hectares, that's about 65,000 acres of wetlands to protect the wetlands. That's what they are. Only they're not allowed to call them wetlands. So you'll never see the agency, I won't mention, refer to them as wetlands, but they're wetlands. Does that look like a wetland? It does to me. So they're called STAs. Well, whatever. Okay. So, but the cool thing is, no matter what we call them, they're working. The red is the inflow and the blue is the outflow in concentrations of phosphorus in micrograms per liter, but we're fond of calling it parts per billion. It's the same thing. The units are exactly the same. And the water's coming in at anywhere from between 100 and 200 parts per billion, and going out as low as 15 to 60, depending on the wetland. And that's what they're trying to determine, why some work and some don't. They have a long history on some of them. This is the STA-1W that's over near one of the closer ones to West Palm Beach. And for 15 years, 20 years now, and it's the data continue, the outflow is exceedingly cleaner in phosphorus than the inflow. They're working. God bless the South Florida Water Management District for this. And I said that publicly. You can tell them that. And they fit, and the design was great. Their loading rate is not excessive. It matches a publication we did in the year 2000 perfectly, that their loading rate is about 1 gram, that's a tiny amount of phosphorus, per meter square per year going into those wetlands. That's why they're so big. And they work. And we had suggested in our paper 1 to 2 is a real safe range. If we even look at the last 5 years of that, well, it's not the last 5 years now, but it was. The average inflow for this STA-1W, which we'll talk about in a minute more, was 191. The average outflow was 35, 82% reduction. Wonderful. Great. They work. Not so fast, my friend. The federal government, in its infinite wisdom again, mostly the feds, but all sorts of other people were involved in this. And at first I was very skeptical. Said, no. It's got to be 10 parts per billion going into the Everglades. Now, I'll show you an experiment we did. And at first I was saying, come on, 10. That's rainwater. That's rainwater quality. How can you expect Mother Nature in a nice little wetland to do that? That's almost impossible. So I was skeptical, whatever. But that was the goal when we started our research. Turns out it wasn't the goal when we finished it, but that's a whole other story. So 10 parts per billion is the sort of a magic number. How many people have heard that number with regard to the Everglades? Not a lot of you. It's easy to remember. 10. Well, I was told now it's a 3-page document that says, well, it could be 13, maybe 15, could be blah, blah. It goes on for 3 pages of blah, blah, blah. I like 10. It's simple. And it's doable. And this is how they calculate it, by the way. They went out into the Everglades and what are called the water conservation areas 1 and 2. You know where those are? They're north of the park. Took a bazillion samples. I don't know if they did it from helicopter or how they got out there without stirring up the water. But they took all these samples and determined after the fact that the 75th percentile of all of those samples they took was 10. In other words, 75% of the numbers were lower, but and 25 were higher. They decided that 75th percentile was what they wanted to use as a standard. And that's what we went into our research thinking about. Anyhow, long story, we published this paper, just got page numbers this year. It's a 2000, that says, you can't read it, it's Ecological Engineering, it's Protecting the Florida Everglades Wetlands with Wetlands. Can stormwater phosphorus be reduced to oligotrophic conditions? Oligotrophic means very clean water. And what we had done was a mesocosm experiment. A mesocosm is nothing more than a little wetland in a tub. The tubs were about 3 feet by 18 feet in size, maybe 20 feet in size, so maybe the size of 2 of these sets of tables together. And we had 18 of them, and we put different plants in. And this was all done, done on South Florida Water Management District with a contract from them on their property and so on. This is what they looked like from a helicopter when I was flying over them once, these little rectangular mesocosms. And we pumped water through them, as this diagram suggests. But our starting point was the outflow of the STA1W that I just described to you, had 35 or whatever parts per. So our starting inflow was the clean water to see if you could get it cleaner. This is what they actually looked like. We tried all sorts of different plant communities. I won't go too much. I've got a list for you, but we'll go through that real quickly. Well, we had sawgrass, cattail, water lily, Eleochris combined, submerged aquatic vegetation, and a control, which first started out as take the plants out every day, and finally it dawned on us, that's nuts. That's impossible. So we called it our self-design. We let it do whatever it wanted to do, and it turned out to be one of the more effective treatments, by the way. So this study started in 2010. I'm not even going to bother to show you the first 2 years of data because they were embarrassing. These mesocosms were exporting more phosphorus than we were putting in. And you can see that even in 2012, the beginning of, let's see, how can I do this? The red line, if you can follow that red line through, the red line is the inflow. That's the water coming out of the STA. And you can see that it's averaging anywhere between 20 and 30. In fact, it turned out to average 25 for the whole study, our inflow water. So for these to be effective treatments, you got to get below 25, don't you? Well, just about, you can see sort of a shifting that occurred in this November, December 2012. Now, remember, we started this in 2010. And for the longest time, they were exporting. Why were they exporting? Because the soil we used was still not finished exporting. It was still an efflux from the original soil we used, which was not very polluted, but it was polluted enough. So that point alone, we showed that it would if they did build new wetlands to take from 30 to 10, let's say. That's what we were looking for. Can we get from 30 to 10? That it would take 2 years before they even worked. So you'd have to be patient. All right, but it did flop, and then all of a sudden, no, not all of a sudden, but about in December, January, February, March, the outflows were routinely lower than the inflow. Again, the red line is the inflow. You got to follow that red line to make sense of this. And lo and behold, just when the study was ending, just when our contract was over, just when I gave a final report to the district and then went up to Ohio for the summer, just when, boom, boom, everything was done, we hit 10. In fact, 2 of the wetlands hit 10. One of them was at 9 for a couple. And that's where the project ended. Now, what's your reaction to that? Shouldn't we have continued it for another year? Put 3 years into it. Well, if truth be told, we did take samples for them for free. We had a contract. They didn't sign it in the very end when it went up to the totem pole in the South Florida Water. We still don't know why they rejected the funding for that. It was so obvious we needed another year or two. So obvious. We had the golden apple in our hand and we couldn't verify it. That's a whole nother story. It was like, Bill, welcome to Florida politics. Science and politics are very strange bedfellows down here. Anyhow, we did prove that it could happen, and I bet that's about all we can say. And we did, and by the way, the one that was the most effective, interestingly, was a combination of submerged aquatic vegetation and water lilies. Excuse me, that's what's growing out in the wetlands to begin with. There's tons of, that's what's out in the wetland in and among the sawgrass. So it makes a lot of sense that was the winner, if you want to call it that. So we got some, I won't belabor these little phosphorus budgets. And again, even though we didn't continue the project because the contract was all of a sudden pulled out from under us, Sierra Club got a hold of our paper, and boy, they got all excited. And this is a guy who just loves to write, and I don't know where he wrote. He sent this in an email or something. He gives me permission to write it. For those of you who think I have engaged in hyperbole as regards to my claim that the South Florida Water District systematically underdesigned the STAs. So the Sierra Club's been arguing that they're not big enough yet. Here's a hot-off-the-press analysis by William Mitsch, formerly at Ohio State University, now Florida Gulf Coast University, et al., who, in a paper, Protecting the Florida Everglades Wetland with Wetlands, et cetera, concludes the following, and he put our conclusion word for word, saved me the trouble of doing it. Achieving 10 parts per billion concentration consistently from created wetlands in the Florida Everglades remains problematic. We were very cautious as scientists say it just ain't a done deal. We hit it once, we need more data, we need to start this study over and run it for 10 years. But this research confirms that it may be possible with low loading rates, the right vegetation communities, and low nutrient soils. So all we said was it might be possible. Well, I hate to tell you how many, well, never mind, I don't want to go into it. There's in universities, college students have food fights. Once in the scientific world, we have the equivalent of food fights with journal articles instead of throwing food at each other. So there's a food fight going on right now. But he went on, it's highly unlikely the addition of 6,600 acres, and then he goes on to say this is what they're planning to do. So anyhow, the Sierra Club really liked what we said. Many other organizations like the Everglades Foundation seem to appreciate it, but there we are. We're right on this question now. Do we shoot for 10 or not? The Miccosukee Indians are very adamant. They want 10. Not 11, not 12 and sometimes 10, because that's what was the original goal, and it seems to be changing all the time now with sort of a moving target. Anyhow, that was Larry Fink that wrote that. Okay, I've talked long enough. That's where the phosphorus story is right now. Stay tuned. There's all sorts of new papers coming out, both pro and con to what I just told you, and we'll see. But my conclusions, if I have time, do I? Okay. Wetlands can be designed to remove significant amounts of nitrogen and phosphorus from agriculture and stormwater runoff. I just believe that. And concentrations on the order of 20 to 30 parts per billion of total phosphorus, so I'm not saying 10, and 1 part per billion total nitrogen are reasonable expectations. But lower concentrations can be achieved. While 10 parts per billion of phosphorus treatment is a challenging goal for the Florida Everglades, it may be possible. For stormwaters from the EAA, that's Everglades Agriculture Area, to achieve those low levels, if extensive wetlands downstream of the current stormwater treatment wetlands are, see, that was the rub. Here's Professor Mitsch publishing a paper said, well, you got 30, good for you. If you build a ton more wetlands downstream, you can get 10. That's what we were basically saying. And that didn't fit the program. But I also agree that another strategy is to simply recognize that the water conservation areas, now that's where the cattails were coming in that caused this crisis to begin with. But the water conservation areas are taking phosphorus out as well, and just assume that they are now not pristine wetlands, but blue-collar, hard-working wetlands, they can take it down to 10, thank you very much, and we don't have to do a thing. And the park, at least, will be protected. So we can just stop right now and say, they created some wetlands, and oh, by the way, the wetlands that are in water conservation areas 1 and 2 or whatever are taking it down to 10, and we should all be happy and go have a beer. So I'm saying you don't even have to build any more wetlands, you just have to recognize another function for those water conservation areas. But there are a lot of people saying, oh, no, we can't do that. So we don't want any cattails, no cattails. So purchasing additional lands for water storage south of Lake Okeechobee may benefit downstream water quality, but it may not be the answer, and this is what I was saying this long before this purchase issue came up, the answer to achieving extremely low phosphorus concentrations. It's just not the answer. And any reservoirs built to supplement, I go crazy when they say, oh, we're building a reservoir. Anybody else feel kind of queasy about that? All they're doing is creating big ponds that are going to be green as a golf course within years. And they'll be heavily managed and all that. So this idea of building reservoirs to store Lake Okeechobee water, newsflash, we got Lake Okeechobee. That's where the water is supposed to be. I'm sorry, these reservoirs will be eutrophic nightmares in themselves when they're built. They will be added to that list of 760 sites for sure. The fact that wetlands do improve water quality and sequester carbon sustainably does not automatically mean that they will be implemented. That's the bizarre thing about this. The fact that they work, there are large land requirements. I'd say that's the 800-pound gorilla. You have to have land for wetlands. That's just the way it is. And some land managers still fear committing to wetlands for a variety, all sorts of non-scientific reasons. But my take-home message always in my talks is pretty much the same. Wetland restoration and creation are not easy, but they require attention to Mother Nature. The Mother Nature is that self-design. You've got to let the wetland design itself. Even in our mesocosms, we let it design itself after we planted it. And Father Time. That is, the new wetlands take time. So Mother Nature and Father Time are the parents for a healthy wetland if you get into this business. Okay, well, I'll just give a couple commercials here. All of this and tons more is in the brand new wetland book that I just published, 5th edition of Wetlands. It just came out in March. I've got case studies on the Everglades, case studies on everything I talked about in great detail, and a whole bunch more. But, and we're in the 5th edition. Jim Gosling and Jim tragically died just as this was being published, but I'm carrying this 5th edition, and who knows, we might do 6th edition. But we've got, what's really cool is because I moved to Florida, I put Florida on the cover. That is a tidal creek off of Naples Bay. And we're also teaching short courses. My assistant Lee Zong put a bunch of flyers back there. I get some of the best people in the country to come down here. It's not hard to convince them to come to Florida, or they're already down here. So we're teaching a river restoration course. Okay, some of our students will be in the class, but basically this is for anybody who wants to learn about these subjects. We have a course on river restoration in November and one on wetland restoration in April. April one was with Robin Lewis, that I'm sure many of you know. He's sort of an icon down here in Florida. Anyhow, we do those things as sort of outreach, but also teaching requirements, and so that's our program for Naples for this year. And thank you very much.
In the course of this discussion, it seems to me that you've kind of tiptoed around the issue that this is really sequestration of phosphorus and not removal of phosphorus. You're sequestering phosphorus in these manufactured wetlands, but it's still there.
Yes.
So basically, when that vegetation that is sequestering the phosphorus eventually decays, it'll be releasing it back into the natural flow of water. And in the case of politics discontinuing these wetlands, there will be a huge slug of phosphorus released to flow down into the Everglades. Is that essentially your views of it?
You're correct in a geological scale, but in the hundreds of year scale, those can continue to be sinks. I'm very impressed that the STAs continue to be sinks after 20 years. That's also what we found in Ohio. In fact, we found the wetland sort of turning the corner and getting better in the last couple of years. You know, it's getting more mature. The ultimate question, yeah, what do you do with these wetlands after 300 years? Okay. It's not that the phosphorus concentration will be high, it's just it'll be deep. You know, there'll be sediments accumulating either from the plants or from the inflowing sediments. That's especially true for phosphorus. Nitrogen, at least a lot of it can go off to the atmosphere. There are all sorts of clever ideas that we have, and I think that's one thing that the Everglades Prize was asking for is, okay, how do you take the phosphorus out and get it back to agriculture? And if I gave my secret, you'd all run off and get $10 million. But it's so simple. It's so simple. But yes, I understand what you're saying. We have to have an adaptable landscape. But I'm truly amazed that those wetlands called STAs are continuing to work very well. And it's because they're not overloading them. The stories, when you hear, oh, the wetland's exporting phosphorus after 5 years, that's because it was very poorly designed and they're putting too much in. But if you're gentle, you know, 1 to 2 grams per meter square per year is nothing. That thing can last a long, long time. But it requires land that we call wetlands.
Sir, I have a question.
Yeah.
So you've been talking about phosphorus and either sequestering or removing phosphorus before the water gets to Florida Bay. Has anyone been looking at the nitrogen and what that might look like when the water hits Florida Bay for this
Well, that's the interesting thing. Now, I'm talking about way before it gets to Florida Bay. We're talking about before it gets into the Everglades proper. But you're absolutely right. As we illustrated, nitrogen's a problem once it gets to the coastline. That's the beauty of a wetland solution. Now, if you had an environmental engineer, they'd come in and give you all sorts of solutions for taking phosphorus out, and you'd get 98% removal, and then all of a sudden people would say, hey, we got nitrogen. And the engineer would say, well, you didn't ask me about that. Mother Nature's a little more flexible, and so for sure, our mesocosms and for sure the STAs are taking nitrogen out as well, for sure. It might be 10 times the amount of phosphorus. I don't have a number, but it's absolutely happening. So that's the nice hedge bet you get when you use nature to solve a problem. She knows that Redfield ratio. She's got it memorized. And she can do just fine with nitrogen, even though we design it for phosphorus.
Which agency insists on using STA? Corps of Engineers or Water
Which
Management?
agency?
STA. The
built them?
stormwater, yeah,
Yeah, that's South Florida Water Management
South
District.
Florida. And which agency is proposing the reservoir solution?
Drinking water?
No, the reservoir you showed up there to augment Okeechobee. Who is proposing that?
The Okeechobee.
Water Management District.
Well,
On
they're
one
not-
of your last slides, when you said someone is proposing a reservoir,
Oh, South Florida District.
South Florida.
They kind of, any district people here? I don't mean this in a disparaging way. They rule the roost. They control your water, quantity and quality. So it's usually going to be South Florida Water Management District. A little bit of Army Corps, but mostly it's South Florida District.
If you were the governor of Florida, how would you regulate the sugar industry?
Are you letting me be governor? I just have to say your time's up. No, I mean they've had free use of our environment for so many years, and no corporate entity should be able to get away with what they've gotten away with all these years. And I say that I come from the Ohio Valley, and I was brought up in the steel industry, and that's all shut down, a lot of it because of environmental conditions. And I said, well, that's just the way it is. So I don't know why we keep treating agriculture as a holier-than-thou industry when all the other industries that I know of either had to shut down or clean up. So that's what we would do. Now, the fact that we taxpayers are paying for those STAs, I'm greatly offended by that. Those should have been paid for by sugar. It's their pollution. And I'm not just saying sugar, whatever agriculture entities are in the basin. I mean, think about it. They're creating the pollution and you're paying for it to clean it up. That just shouldn't be. The cost should, now maybe they're giving donations to the district or something under the table or over the table, I don't know, but really it's their responsibility to, if they want to be good citizens of the state of Florida, is to clean up the messes they make.
Well, with that, we'd like to thank
Okay.
Dr. Mitsch for his presentation today.